In 2008, Kent Beck wrote this wonderful book, Implementation Patterns. It's full of tips and techniques that programmers can use to keep their code nicely structured and well ordered. But he began this book with what I consider to be a striking statement. He said, "Actually, this book is built on a rather fragile premise that good code matters."
Fragile? Fragile? I don't see anything fragile about the fact that good code matters. Of course it matters. What nonsense to think otherwise.
Of course, as the author of this book, Clean Code, I have to agree. Clean code matters a lot.
Indeed, clean code can make the difference between the ultimate success or failure of your company.
I've experienced this quite directly. Here, let me tell you the story of the company killed by code. In 1988, or thereabouts, I was working for a company, and we were building a large network management system in C. We purchased a debugger from a company named Sword. It allowed us to single step and breakpoint our way through our C code.
Whoa, I've got to debug my Ruby source code all the time,
Yeah, but back then, a source level debugger was a rarity. I mean, most of the time, we debugged in hex.
Yeah, that sounds like a nightmare.
Oh, it was. Of course, it's all we knew, but it was. But look, this Sword tool was great. I mean, it was very powerful, and it saved us a boatload of time and effort. We loved it.
Gosh, Uncle Bob, that must have been a really popular product back then.
Oh, it was. I mean, they were doing a gangbuster business at first. The trade journals loved them, and the folks at user groups and conferences, they couldn't get enough. A couple of years later, it was 1990, and we started dreaming about switching from C to C++. We called Sword and asked them whether they'd be supporting C++ anytime soon. They told us that the C++ version would be coming pretty soon. But time wore on. For 6 months, it wore on. But finally, the C++ version of the Sword debugger arrived. We were really excited! And so we installed it and we fired it up. But it took 45 minutes to load, and then it crashed.
Yeah. Boom.
Well, we didn't think it was so funny. Debugging C++ in hex is not an awful lot of fun. So we called up Sword and we told them they had to fix this problem, and they swore to us that they'd fix it in the next release.
Yeah, and I bet it took them another 6 months to send you a new release.
Yes, Jerry, it did. And believe me, our patience was growing mighty thin.
Yeah, and then when you got it, it still took 45 minutes to load and then it crashed, didn't it?
Yes, Jerry, that's exactly what happened. Needless to say, we canceled our license and got on about our business. From our point of view, that product was dead. We interrupt this program to bring you a special news bulletin. Sword Inc., famed creator of the very popular C debugger, has declared bankruptcy and closed its doors forever. We now return you to your regularly scheduled program. Yeah, it was just a few months after that disastrous second release that the company tanked and the product disappeared. But that's not where the story ends. A decade later, I was at a C++ conference, and I met one of the developers who used to work at Sword back then. I asked him what happened, and he told me the story.
Son, when we first started that project, those yahoos in marketing told us we had to be first to market at all costs. If we weren't first to market, then there was no point in even getting started. So we rushed, son. We rushed like a horse in a raging brush fire, like a rabbit running from a snarling wolf. We rushed, and we made one hell of a mess. When we were done, that code looked like a whole herd of hungry hogs had stampeded through it. I tell you, son, it was a miracle that code worked at all. And getting it working, well, that was a bunch of bailing and hailing and hooking and crooking and duct tape and all kinds of shenanigans. But we got it working, son. We got it working just by the skin of our teeth. Of course, then it was all we could do to keep it working, son, 'cause there was always another bug fix or some high-priority feature that customers kept on wanting to write bigger and bigger programs and go faster and faster. So we kept right on rushing, son. There was no time to go back and clean nothing up, 'cause there was always some new thing, some maximum priority thingamawhat's some customer who had to be satisfied. We never managed to clean it, son. And then, son, why, they dropped a motherload of horse manure on the fan. They told us we had just a few months to get the whole thing working with C++. C++, son, do you know how hard it is to parse that language? Well, it ain't easy, let me tell you. Now, we looked at that, we said that was just impossible. That code was already a mess. It was more tangled than a haystack in a tornado. Oh, we tried, son. We tried, all right. We worked on that like a mare giving birth to a full-grown stallion. We worked in the mornings. We worked in the evenings. We worked on the weekends. We worked and we worked and we worked. And we failed, son. We failed. We couldn't make that tangled mess of code parse C++. It was a consarn disaster, son. And the reason we failed was because we rushed in the first place.
Okay, I admit it, I embellished that a little bit, but not actually by very much and not in any substantive way. What the guy told me was that they rushed that C product to market and made a huge mess in doing it. And then they couldn't transition to C++. They saw their C market dwindling away out from underneath them, and they couldn't follow it into C++ because of the mess they'd made in the code.
It would appear that Sword Inc. was destroyed by its own bad code. At least in their case, the premise that good code matters was not fragile at all. Yeah, okay, sure, but like, why? I mean, what was it about the bad code that killed them? Have you ever worked on a greenfield project? Do you remember how productive it was? Do you remember how lightning crackled from your fingertips as you got feature after feature working?
Yeah. I could just blast a whole bunch of features together in just a few hours. It was fun.
Yeah, man, they would come to me and they'd ask me for a feature and I'd have it ready for them that same afternoon. And so they really thought I was a hero.
Yeah, I'm sure it felt like you were going real fast. But it didn't last, did it? As the months went by, I'll bet you started feeling slower and slower until you were barely crawling. That's what happens to projects. They start out fast, but then after a few weeks or months, they slow way down. And why? Because there's a mess building in the code. The more that mess grows, the harder it becomes to add new features or change existing code, until finally
Things that would have taken you days at the beginning now take you weeks or even months.
But now, think of it from the manager's point of view. They saw how fast you were going at the start, and they laid their plans based on that speed. They made promises to customers based on that speed.
They don't understand why you've slowed down. All they understand is that now they're looking at this very scary gap. A gap that's costing them a lot of money and forcing them to break a lot of promises.
What would you do if you were one of those managers and you saw your carefully laid business plans going up in smoke because the programmers had inexplicably slowed down? What would you do if you saw the profit you expected turn into a huge loss because the programmers were going so slow?
I would remind them of the mission and suggest that they find a more intelligent way of working.
Gosh, Uncle Bob, I think I'd just kind of sit them all down for some coffee or maybe some herbal tea and ask them what their issues were. In the end, I think I'd probably end up begging them to go faster.
Well, I'd tell those lazy slackers to get moving. I'd tighten their deadlines, I'd mandate overtime, and if any of them complained, I'd show them the airlock. Of course, none of that is going to do a bit of good because the problem is not that the programmers aren't working hard. They are. The problem is that the code is slowing them down. So the harder they work, the slower they'll go.
And so, despite the pressure, the threats, the deadlines, and the overtime, the productivity still dwindles, and the scary gap looms ever larger.
It seems to me that the solution to this problem is to hire more programmers. After all, if you double the staff, you double your speed. Well, not quite. You see, there's this thing called Brooks' Law, which states that adding manpower to a late project makes it later. It works like this. The team is working along at this level of productivity, and then we decide to add more staff. The productivity plummets for a few weeks or months as the new people suck the life out of the old people, but then the new people start to get smart and their productivity rises. In theory, it should rise above where it was before. Except for one small logical flaw. Precisely who is teaching the new people? The people who did this! And it's not just the old people teaching the new people, it's the old code teaching the new people. The more the new people read through the old code and deal with the old code, the more they realize how things are done around here. And so they emulate the behaviors that made the mess in the first place, and of course the mess continues to grow. And so all hope of increasing productivity is dashed as the increasing mess overwhelms the new staff and the productivity resumes its inexorable downward trend. Except now the business is spending much more money on that new staff. And so the scary gap has gotten quite a bit scarier, hasn't it? Right. Cash flow increases by a step function when you add new staff, and the decreasing productivity makes that scary gap that much scarier.
Yeah, maybe that was a fluke. Let's try it again.
Indeed, lots of businesses try this many times because, after all, the definition of sanity is to repeat a failing strategy until it succeeds. But of course it doesn't succeed, and so the scary gap continues to grow and get scarier and scarier. At this point, it might be wisest to consult with the programmers themselves. They are closest to the problem. Perhaps they have a solution.
Oh yeah, sure they do. You want to guess what it is?
Yeah, start over. Throw it all away. Redesign the whole thing.
Yeah, the best thing that could happen to this system is for someone to walk into the machine room with a great big magnet.
Oh, Uncle Bob, I want to be the architect. Can I please be the architect?
As you might imagine, this idea thrills the programmers, but terrifies the managers. The managers know how much money was spent on the first design, and the thought of spending all that money all over again chills them to the marrow. What's more, they've got no confidence at all that the redesign is actually going to solve the problem. But here's the thing. What other choice do they have? I mean, they've tried everything else they know to do and nothing worked, and they can't go on the way things are. So as scary as this option is, it's kind of the last chance they've got. And there's one other factor. Programmers, you should never underestimate your power, because you are the ones who know. Managers don't. They aren't the ones who know. You know. You were hired because you know. So if you beat the drums for a redesign, as much as the managers might not like it, you will eventually win because the managers understand that you're the ones who know.
Oh, yes, you'll win all right. And it will be a disaster.
And what a disaster it'll be. But it doesn't start out looking like a disaster. Oh no! On the day that the managers announce that we're going to redesign the project, a cheer goes up from the development organization. Hallelujah! We're going back to the beginning. We can be productive again. We're going to leave this mess behind. We don't have to live in the old code base anymore. Of course, the next day, in the cold light of reality, we realize that we are not going to be the ones who will be redesigning the system. Management has picked the 10 best, the Tiger team, the ones who made the mess in the first place. They're going to be the ones who will sit in a room working on a greenfield project on the new design. They're the ones who are going to lead us into a bright new future. The rest of us hate those guys. They're off doing some greenfield thing while the rest of us are stuck maintaining the old system. Because after all, customers aren't going to wait months or years for new features or bug fixes.
And now, just where do you think the Tiger team is going to get their requirements from? You don't actually believe there's an accurate requirements document, do you?
No, man. I mean, there's been way too many late night fixes and midnight modifications for that.
Yeah, the requirements aren't in a document anymore. Now they're buried in the old code.
That's right. The requirements are in the old code. So that Tiger team that's supposed to be taking us into the future, they're spending their time poring over the old code, trying to figure out just what it is that the old system does. And then they're trying to figure out how they can reorganize and repartition that code so that it'll be better by some definition of better. Meanwhile, the rest of us are working like dogs to fix bugs and add new features. So while the Tiger team is off studying the code, we're busy changing it out from under them. The logical implication being that the two factions are in a race. Right, a race. And just like Achilles and the tortoise in Zeno's paradox, every time the Tiger team got to where the old system was, we would have moved the old system on with new features and new fixes.
And while it is mathematically possible to prove that Achilles will eventually pass the tortoise, that doesn't seem to work in software.
I once worked for a company where that race went on for 10 years. 10 years after we started the redesign, development was still going on and we were still shipping the old system. Eventually, in desperation, the managers decided to replace all the old systems in the field with new systems, even though the new systems couldn't do everything the old systems could.
I would imagine that the customers were rather unhappy about that.
Yeah, some of them were pretty upset, but that was nothing compared to the developers. You see, the Tiger team had long since gone on to bigger and better things, and the programmers that had replaced them were racing like mad to keep up with the old system. They were horrified at the idea that they'd actually deploy the new system. They said, "You can't deploy this, it's crap, it's got to be redesigned." The big redesign in the sky is almost always a failing strategy. Oh, it might work for a small thing of a couple of man-months or so, but for big projects it's almost certain to end in horrific waste and ultimate disaster. So that's how bad code can destroy a team, a division, and even a company.
And so here's the bottom line. You cannot deal with a mess by running away from it. The only way to effectively deal with that mess is to turn around and face it, and find the rot and clean it.
What happens to software over time? Why does it rot? Why do the beautiful designs we start with so often degrade and rot into a festering pile?
At the moment of inception, the design of a software system is usually a simple and elegant and beautiful thing. And likewise, when we first write the code, that code is simple and easy to change and elegant, and our hopes for the system are high. But with time, that code will start to rot like a piece of bad meat sitting in a hot barn, and the stink will get so bad that not even the hogs and crows will go near it. You can tell how old a piece of code is by the facial expression of the developers as they bring it up on their screens.
Before we investigate why this happens, let's study that stench in more detail. What is it that makes bad code smell so bad? Rigidity is the tendency of a system to resist change.
A system is rigid when that system requires us to make many changes to many different places in order to fix a single bug or add a single new behavior. Such a system resists change, and so we say it is rigid.
I'd really appreciate an example.
Sure! Let's not just say that your boss comes to you one day and shows you a bug report and asks you if you can fix it. You look at that bug report and you realize you know exactly where that bug is. You know the line of code that bug is on because you were just in that module a week or two ago. And you know how to fix it too. It's gonna be easy. It's gonna be easy peasy, simple as pie, no problemo. So you give your boss the minimum estimate, 3 weeks. He goes away happy because he got the minimum estimate for that task. Now you go to that module and you scroll down to where you think that bug is, and sure enough, there it is, right like you thought it'd be. So you reach right in there and you fix it. And you're about to go do something else so you don't give your boss the idea that your minimum estimate was a little bit too long. But then there's this itch at the back of your head. Something's bothering you about that change, son. And that's when you realize that the change you just made to that module is going to break a different module in the system. So you plop back down and bring that other module up on your screen and scroll to the place where you were thinking about, and sure enough, you find a problem. The change you made to the first module is incompatible with the second. So you reach into that second module and you fix it. And now you know what's coming, don't you? Because sure as rain on a sunny day, there's other modules in the system that aren't simpatico with the change you just made to that second module. So now you start going from module to module to module, fixing issue after issue, trying to force the system back into a consistent state. You're like a dog chasing his tail, burning lots of energy, but you're not getting anywheres.
And so the weeks will go by. 2 weeks, 3 weeks, 4 weeks, 6 weeks. And then your boss will come by to find out what happened to your 3-week estimate. And you will undoubtedly emit the pathetic phrase that so many software developers have said in the past. It was more complicated than I thought.
Yeah, that's a rigid system. And it shows one of the most frustrating things about rigid systems, their wild unpredictability. Estimating a fix or an enhancement is fraught with error because it's impossible to properly determine the number of modules that will actually be changed. And so rigid systems blow estimates.
Yeah.
A fragile system is a system that malfunctions in many unpredictable ways when a single simple change is made.
We say that a system is fragile. Then the repair of a single bug or the addition of a single new feature causes a malfunction in one or many other parts of the systems that have no connection with the parts that was changed. I know you want another example, don't you? Well, this here fella's got a good one.
Long ago, I worked on a system that tested telephone lines. This system had 24 ASCII terminals connected to a central minicomputer. The user interface was character-based and menu-driven, and the menus were hierarchical. Deep down in one of the submenus, there was a grammatical error. The word progress was spelled process. We all knew about this error. We all cringed whenever we saw it, but there was never a good reason to fix it. Then one day I was working in a module and I happened to scroll past the string for that menu. It was an easy thing to change, so I changed it. I felt pretty good about that too. Of course, I compiled it and I tested it. I brought it up on the screen to make sure that it fit and there weren't any other issues. And there weren't. And so I added it to the list of changes for the next release and I shipped it. Hundreds of systems started crashing in the field. Not our systems, our customers' systems, but they blamed us anyway. We had customers on the telephone, we had managers rampaging around pointing their fingers at people, we had programmers hiding under their desks. What I had forgotten was that in their infinite wisdom, our marketing department had told our customer that the best way to interface their systems to ours was to plug their computers into one of our RS-232 terminal ports. Of course, that meant that the customer's software had to parse our menus. So when I changed that menu, it broke the customer's software. My boss came to me and said, "What the hell did you do?" And I said, "I fixed a spelling error." And he said, "Well, don't ever do that." And so a fragile system is a system that breaks in unintended and unpredictable ways when simple changes are made. Such systems are terrifying to managers and customers because they are so wildly unpredictable.
Indeed, when systems are fragile, customers and managers come to the conclusion that the software developers have lost control of their software and don't know what the hell they're doing.
An inseparable system is a system in which those parts that might be profitably used in another system cannot be separated out
from the first system.
Indeed, this says that a system is inseparable when the various parts of that system cannot be independently reused in some other system. Let me give you an example. Let's say that I need a new car, and I got very specific requirements for this new car. It's got to be silver, it's got a seat 6, and it's got to go 200 miles an hour. That turns out I talked to my brother-in-law and he's got the car. It's silver, it's seat 6, it goes 200 miles an hour. What's more, he just lost his license, so he's gonna give it to me for free. There's just one catch. My brother-in-law's car's got a trailer. And this trailer ain't coupled to the back of the car with no hitch, no sir. That trailer's welded onto the back of that car. The rear brakes have been taken away from the car and put on the back wheels of the trailer. The rear lights have been put on the back of the trailer. The trailer is part of the car. Now, I got me a really small garage. And that trailer car, well, it just ain't gonna fit in that garage. So I gotta get rid of the trailer off the back of that car. I go take it to a mechanic. I say, mechanic, take the trailer off the back of this car. He looks at me like I'm crazy. He says, you can't take the trailer off the back of this car. That trailer's part of the car. It costs you lots more than buying a new car. And what's more, I'm not guaranteeing my work.
To continue this example, your boss comes to you one day and says, you know that module you got to write? Well, there's this guy, Joe, one floor below us, who wrote a module just like it about a year ago. You should go talk to Joe and see how much of that module you can reuse. Now, you know Joe, and you know the kind of code Joe writes. So you're not really anxious to go wading through his code to see if you can use any of it. But your boss asked, so you have to do it. So you get the code from Joe and you look it over. And sure enough, it does exactly what you need. But it's got a trailer. Joe's code does a lot of things you don't need. And you realize that the time and effort required to decouple Joe's code so that you can take the stuff you want and leave behind the stuff you don't is so large that you might as well just write the module yourself. So you go back to your boss and you tell him that you can't use Joe's code because it's inseparable.
Inseparable systems are unpredictable. You never know if you can reuse the components in the system, and so the changes cannot be reliably estimated.
Opacity is the tendency of a system to be so ineptly structured that no amount of effort can be applied to divine the author's original intent.
We say that a system is opaque when reading the code tells us little or nothing about what the system does or the way it works. What they're trying to say is that the code looks worse than a pigsty in a rainstorm.
This picture really says it all. Opaque code is hard to read, hard to change, hard to understand. Raise your hands if you've ever been significantly impeded by bad code. And you guys out there on the other side of the screen, I see you out there. Get your hands up, because we've all been impeded by bad code, significantly impeded. The question is, why did we write it?
Stupid managers.
You know, like, man, we've had some really impatient customers, and well, they just couldn't wait.
Oh, Uncle Bob, we just have impossible schedules.
Excuse me, but those are just excuses and cop-outs. It's your fingers on the keyboard. It's you that rots the code. It's you, not them.
Sherlock's right. The only reason the code goes bad is because we ruin it. We're the ones who make the mess. We rot the code.
Yeah, but we gotta go fast. And that's the only way to go fast.
Yeah, my customers will never give me the time to do things the right way.
Yeah, Uncle Bob, we need to go fast, and that's why we make the mess.
I understand. You feel the pressure of the deadline and the urgency of the customer, and so you rush. But whenever you rush, you make a mess.
Yeah, but dude, we can always go back and clean it later when we're not in such a hurry.
Go back and clean it later? Go back and clean it later? Would you please tell me the last time you went back and cleaned it later?
It doesn't happen. We all know that. Deadline pressure doesn't suddenly get less. Customers don't suddenly get more patient. Urgency never diminishes. Schedules never really relax. We all know that saying that we'll go back and fix it later means we're never going to go back at all.
The irony is that making messes is not the way you go fast. It's the way you go slow. And you already know this. You've acknowledged it. You've said you were significantly impeded by bad code.
If you want to go fast, you have to stay clean. The only way to go fast is to go well.
This can be hard to accept because most of us feel like we can get done faster by rushing. The truth is, though, you can't. If you rush through code, you will always slow down.
Now, some people think that they can go faster in the short term by rushing, even if that slows them down in the long term. But this is an illusion. Rushing always slows you down, even in the short term. Making a mess is never a strategy to go fast. The only way to go fast in the short term or the long term is to be clean.
Ah, Grasshopper. Have you ever watched a sushi chef prepare food? The next time you go, pay close attention. You can tell that the chef has practiced his moves. Every motion has a purpose. Every motion is sure and quick. Every motion is precise. He cuts, he slices, he rolls, he positions in a flurry of concentrated activity. And then comes the magic moment where he takes the dish and he puts it in front of you. The presentation is impeccable, but Grasshopper, look at his workspace. His workspace is clean and spotless. He has been cleaning throughout the entire procedure because, Grasshopper, that is the only way he can go fast.
What is clean code? I asked several experts that question, and here's what they said. Jonas Strustrup, the inventor of C++, said, "I like my code to be elegant and efficient. Clean code should do one thing." Elegant code is code that does a lot in a few words. Efficient code is code that uses very few CPU cycles. But what does it mean for code to do one thing? That's something we're going to talk about in an upcoming episode. Grady Booch, the author of this 1990s classic, Object-Oriented Design and Analysis with Applications, said, "Clean code is simple and direct. Clean code reads like well-written prose." We understand the simple and direct part. That doesn't need a lot of explanation. But
What does it mean for code to read like well-written prose? Is that even possible? The simple answer to that is yes, it's possible. The slightly longer answer is, well, almost possible. We'll actually have a lot to say about this in the next few episodes. Michael Feathers, the author of Working Effectively with Legacy Code, said, "Clean code always looks like it was written by someone who cares." What a lovely remark. Wouldn't it be wonderful if all the code we read looked like it was written by someone who cares? Have you ever read code that looked like the author didn't care at all? This course is going to be about learning how to care for our code. Ward Cunningham, the inventor of wikis, the inventor of more things than I can mention, the mentor of most of us, he said, "You know you are reading clean code when every routine that you read is pretty much what you expected." It's very much like Ward to say something so profound using words that sound so innocuous, but think about it. When is the last time you read code and thought to yourself, yeah, this is pretty much what I expected? Wouldn't it be nice if we could all learn to write code that was pretty much what we expected? And in fact, that's what these videos are about. How to write code that others will think is pretty much what they expected. Robert Baden-Powell, the father of the Boy Scouts, left a posthumous exhortation to the organization he founded. He told them, "Leave the world better than you found it." Now, what if we did that with our code? What if we left our code better than we found it? What if every time you checked a module in, you checked it in just a little bit better than you checked it out? What if you always did some random act of kindness to the code so that it would be better and better, and you never ever checked it in worse? If we all did that, then our code would simply get better and better and better with time. And that, too, is what this course is all about. Well, that's it. That's our remake of episode 1. I hope you enjoyed it. And if this is the first time you've watched an episode, well, you've got a lot to look forward to. Episode 2 is all about choosing good names. Episodes 3, 4, and 5 are all about functions and function structure. Episode 6 is a two-parter on test-driven development. Episode 7 is about architecture. And then we start getting into the solid principles, and then the component principles, and then advanced test-driven development, and we have just scratched the surface. There's a lot more coming. In 1908, Henrietta Swan Leavitt, an astronomer working at Harvard, made an incredible discovery, one that would change astronomy forever. Astrophotography was just coming into its heyday. Astronomers were producing so many photographic plates that they didn't have time to analyze them all. Back then, women were not allowed to operate the telescopes, but they were deemed capable of making measurements on photographic plates and doing calculations based on those measurements. Leavitt, who initially worked for no pay and was later paid 30 cents an hour, was asked by her boss, Edward Pickering, to study and measure variable stars, stars that change their brightness over time. Finding and studying variable stars using photographic plates is not an easy task. You begin with one photographic plate that has hundreds and hundreds of stars on it, and then you measure each individual star's brightness by measuring the diameter of the spot on the photographic plate. And you do this for every star on the plate.
And then you get another photographic plate from the same part of the sky, taken at a different time, and you do all those measurements again, and you correlate them looking for stars that changed in brightness. And then you do that again and again and again for hundreds and hundreds of plates over years and years. In Leavitt's case, it was the 20 years between 1893 and 1912. And in those fateful decades, she made one of the most amazingly useful discoveries in the history of astronomy. You see, she noticed something peculiar about the Magellanic Clouds. Now, these clouds to the naked eye are just patches of fuzz on the southern hemisphere sky. But on a photographic plate taken through a telescope, they are clouds of millions upon millions of stars. What Leavitt noticed was that thousands of those stars in the Magellanic Clouds were variable stars. Their brightness changed over time. Now, there's a certain kind of variable star called a Cepheid variable. And Cepheid variables pulsate with very regular rhythms. Some of them pulsate once in a couple of days, others will pulsate once in a couple of weeks. Why they pulsate will be a topic of another episode. Leavitt found many such Cepheid variables in the Magellanic Clouds, all pulsating at different rates. But then she noticed something that wasn't true elsewhere. The brighter Cepheid variables in the Magellanic Clouds pulsated more slowly than the dimmer ones. Why would this be true of the Magellanic Clouds but not elsewhere in the sky?
But then it occurred to her, what if all the stars in the Magellanic Cloud were roughly the same distance from us? If that was true, then the rate at which the Cepheid variables pulsated was related to their actual brightness.
She did the math and came up with a simple and beautiful formula called the period luminosity relationship. Given the period of a star in the Magellanic Clouds, using this formula she could predict the luminosity. Or, given the luminosity of a star in the Magellanic Clouds, she could use the formula to predict the period. Now, maybe you're wondering why this was so useful, but let me tell you, it's really useful. And the reason is that if you can measure the distance to just one Cepheid variable star, one that's nearby, then you can calibrate Leavitt's formula to tell you where any Cepheid variable star is. So long as you can measure its period and luminosity, you can calculate its distance. Needless to say, the hunt was on. And it was just a year later that Einar Hertzsprung measured the distance to several Cepheid variable stars. Using those numbers, Leavitt's formula was calibrated such that it could tell you the distance to any Cepheid variable if you could measure its period and its average luminosity.
Let me repeat that. We could now accurately determine the distance to any object that contained a Cepheid variable. What objects contain Cepheid variables? Oh, globular clusters, galaxies, but that's a topic for another day.
For now, just remember that the measuring stick we used to measure the universe itself was the result of the careful and dedicated efforts of one remarkable woman, Henrietta Swan Leavitt. The Scarier Gap, it's named after a man named Fred Scarier. Never mind, sorry.
All right, ready?
No, I'm not ready at all. No, okay.
Action.
Sure. Sure. Let's just say, yeah. Okay, all right. Sure. Yeah. A rigid system and estimating how long. Yes. Okay.
I think after this one we're gonna call it.
Yeah, that's a rigid system, all right, because, you see, rigid systems are wildly unpredictable, and estimating them, trying to figure them out, is fraught with error and frustration because, well, whatever. Because, something. Because you can never properly
The announcement we'll take is fraught with error because you can never properly determine all the parts of the system are going to need to be changed. So rigid systems tend to blow estimates. You were supposed to lip sync that.
Well, I was trying.
It wasn't very successful, I will have to say. Let's do this. I feel good about this next one.
Yeah, do you?
Mm-hmm.
Okay, all right.
Action. That's a good one.
That's a good one, all right. And so rigid systems blow estimates.
Cut. Good job. Except you looked right at me.
Because at the last minute I thought, no, I'm talking about fragile systems.
Oh, you said it.
Yeah, that's a rigid system. And it shows one of the most frustrating things about rigid systems, their wild unpredictability. Estimating a fix or an enhancement is fraught with error because it's impossible to properly determine the number of modules that will actually be changed. And so rigid systems blow estimates.
Cut.
Yeah! Not be predicted. Blah, 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 blah. Grasshopper. Have you ever watched a sushi chef prepare the food? Hello? Hello?